From 0 to base frequency, applied voltage is linearly proportional. Beyond base up to maximum frequency, applied voltage flatlines at 100%. When base is 60 Hz and the maximum is 100 Hz, note the external speed potentiometer 0 to 10 volt analog voltage input is scaled to represent the 0 to 100 Hz range. If one reduced maximum frequency also to 60 Hz, this doesn't really change the performance all that much, besides limiting maximum speed. As previously, from 0 to base frequency, applied voltage would be linearly proportional. Given base frequency happens to be maximum frequency, applied voltage would cease to increase, as would frequency. Really, the only difference between this and our previous implementation is that the external speed potentiometer 0 to 10 volt analog voltage input would now be automatically scaled to represent only 0 to 60 Hz range. Let's see if this is the truth. Navigate to parameter A004, maximum frequency. Select mode. Decrement from the previously saved 100 Hz back to 60 Hz. Then select enter to save it. This motor drive has now been programmed to scale the 0 to 10 volt analog voltage input of the external speed potentiometer from 0 to 60 Hz in 6 Hz per volt divisions. When we start the motor with the external speed potentiometer pegged fully clockwise, excitation frequency ramps up to only 60 Hz this time, as we'd expect. The motor accelerates and speed stabilizes. While the motor is running, we can navigate to parameter D013, output voltage monitor, and find the motor drive is applying roughly 100% of the available line-to-line voltage. When we return to display parameter D001, the output frequency monitor, we can readjust it to provide a 48 Hz excitation frequency, or 80% of the base frequency of 60 Hz. When speed stabilizes, we can navigate back to parameter D013, output voltage monitor, and find the motor drive is applying roughly 80% of the available line-to-line voltage. As we'd expect, applied voltage as a function of frequency appears to be linear, only this time, excitation frequency is limited inside the range 0 to 60 Hz. This particular motor drive is not limited to solely linear volts per Hertz profiles. The Omron 3G3JX-AE004 has available 3 standard profiles. However, one of the profiles can be altered to include a manual torque boost, so I'm saying it's technically got 4 volts per Hertz profiles. The first volts per Hertz profile is the simple linear volts per Hertz profile we just examined. The other 2 are called reduced torque and special reduced torque. These profiles aren't really user customizable and are again defined by 2 points, base and maximum frequency. The transition point for the special reduced torque curve is a function of base frequency being continuously fixed at 10% of the current base frequency. To change among the available volts per Hertz profile, an operator needs to change extended function parameter A044. The volts per Hertz characteristic selection has available 3 options. 00, the default selection, is constant torque. This is a linear volts per Hertz ratio. 01 is a reduced torque profile. Selection 06 is the special reduced torque function. The 4th volts per Hertz profile is actually a user customizable modification of the linear volts per Hertz profile called the manual torque boost function. The manual torque boost function allows an operator to manually select a steeper initial applied voltage slope at lower excitation frequencies for the purposes of establishing an initial burst of current at low speeds. To enable manual torque boost, an operator needs to check 3 parameters. Extended function parameter A041. Torque boost selection has 2 options: 00, the default state, manual, and 01, automatic. Extended function parameter A042, manual torque boost voltage, is user adjustable from 0 to plus 20%. When the setting is at 0%, you've effectively got an unmodified, purely linear volts per Hertz profile. When you increase this setting, you effectively put a little dual slope knee in the volts per Hertz profile. Extended function parameter A043, manual torque boost frequency, is user adjustable from 0 to 50% of base frequency. This is the frequency at which the knee in the dual slope occurs. Let's enable the torque boost function and call it a day. Leave extended function parameter A041, torque boost, in the default 00 manual state. Navigate to extended function parameter A042, manual torque boost voltage. Select mode, increment to plus 20%. Then select Enter to save it. Navigate to Extended Function Parameter A043, Manual Torque Boost Frequency. Select Mode. Increment it to 30% of base, or 18 Hz. And select Enter to save it. When we start the motor drive with parameter D001 displayed, the output frequency monitor, we can adjust the speed potentiometer to provide an 18 Hz excitation frequency. This is our programmed manual torque boost frequency. When speed stabilizes, we can navigate to parameter D013 output voltage monitor and find the motor drive is applying roughly 50% of the available line-to-line voltage. If this motor drive was still using the linear volts per hertz profile without the torque boost modification, we'd ordinarily expect only 30% of available line-to-line voltage, given an excitation frequency of 30% of base. I think this is a pretty cool feature, as should you. Alright, that's about it for this quick applications exercise. We learned to change base and maximum frequency, as well as change volts per hertz profiles on the Omron 3G3JX-AE004 motor drive. We learned this particular motor drive has available 3 volts per hertz profiles: linear, reduced torque, and special reduced torque, as well as a 4th secret bonus torque boost function. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.